Okay, so we are looking at Unit 2, preparing for your assessment tomorrow. I've given you this study guide that's basically running through the equations, running through the pieces that we've talked about here in this chapter. So let's just spend a couple of minutes going through this piece. Well, there will certainly be significant digits that you have to use, right? There will be SI units you have to be able to convert. I would give you the chart, but this is just making sure you know how to do these pieces. If that is still a question or an issue for you, please come see me. Or let's spend some time together. I want to make sure that you're comfortable knowing how to do that. Not many, but there will be some of the pieces you'll have to use in your problems. We talked about position time graphs, how to interpret position time graphs. So, we know that if I have position, well, let me just go ahead and do some drawing here. So if we got a graph here, position would be meters and time, right? Okay? Thank you. That's fine. Thank you. Seconds. Okay? Or distance, if you want to say distance and time, right? Here are my units. If I have a line that looks like this in a distance or a position time graph, what's happening to this person? Position. This is not velocity. This is position time. They're standing still. They're standing still, right? Because over time, their position doesn't change. Does that make sense? Okay? So what would their velocity be? Be zero. Because the slope of a position time graph is velocity. Right? Because velocity is meters per second, right? So in this case, this person is not going anywhere. How about like this? Now what's happening? They're moving, right? In this case, actually moving at a constant velocity. How do you know that? Because it's one slope of a line. Does that make sense? Okay. So that is our position time graphs. And you know that equation, that distance is velocity times time. Or velocity is distance over time. Or time is velocity times distance. Nope, is that right? Divided by. Guacamole, sorry, I got to do it. Time equals distance over velocity. Guacamole, my apologies. Are you with me? This is just moving the same equation around three different ways. All right, acceleration. We talked about velocity time graphs. So now if I do the same kind of graph, and this is now velocity over time. Velocity has what units? Meters per second. Time has what units? Seconds. And you can use any one, but those are the ones we normally use, right? So if I have something that looks like this, the velocity is constant, not changing, right? In this case, we're assuming it's a positive velocity because we're assuming this is positive and this would be negative, right? Okay? So what's the acceleration of this guy? It would be zero. His velocity is not changing. Because remember, the slope of a velocity time graph is acceleration. Okay? How can I determine how far this person moves if I have a velocity time graph? I take the area underneath, right? In this case, it's going to be velocity times time will give me distance. Does that make sense? Okay. So again, for a position time graph, the slope equals velocity. For a velocity time graph, the slope is acceleration. And we said that the area under the curve is equal to the distance or the displacement. Velocity. Yep. For a, again, position time, distance time, the slope is velocity. You had some acceleration equations that you learned, right? Our simplest equation is simply that acceleration is velocity over time. It is change of velocity, of course. So that would be Vf minus Vi all over t. And it is a delta t as well. I just rarely write that because normally we start at 0 with time. You could add a couple of seconds if you wanted to, but normally we start at 0. Okay? And again, here are the problems you did. Numbers 1 through 10, worksheets 1 to 3. I'm encouraging you, use those problems. I'm not giving you the exact same problems, but they should look pretty familiar. Does that make sense? I'm not trying to trick you. I want to just make sure you understand how to do the things I've asked you to learn how to do. And we've got motion with constant acceleration. We've got a couple different equations, 3 different equations that we learned with that. Get myself a new chart here, and again, they're up on the whiteboard here next to us. That velocity final is velocity initial plus acceleration times time. All we did was switch this around, right, to solve for Vf. Our next equation, if I want to actually know distance, if this thing was already moving at some velocity before it started, and I want to know how far it moves, we use xf, and again, this is motion horizontal, is x, vertical is y. xf is equal to xi plus vit plus 1/2 at squared. Understand that squared only goes with time, right? So this part is the motion of its initial velocity, right? Because it's already moving, it has some velocity there before it starts accelerating. If you want to see it in a graph, give me 1 second, Nick. If you want to see it in a graph, oops, I put this in the wrong spot. Let's put this back on this page, my apologies. That we get xf equals xi plus vit plus 1/2 at squared. Your question, Nick? Yes, that's what x is. Yep. Okay? If you wanted to see this in graph form, right, it would look something like this. So here is the accelerated motion, right? But this here is the motion that was already happening because he had some initial velocity. What's that? Sure, right. This would be our horizontal motion, yeah. We're assuming this is going horizontal. But it could, all we'd have to do is just change the letters to y, and we're talking about up and down motion. It's the same thing. It'd be exactly the same. This was assuming that you have thrown something down, not just dropped it. That you added some velocity initially. And then gravity starts accelerating and pulling it down. Good question. Okay? So the green part, that's this. That's what this is dealing with. The blue part of this graph, that's what this is dealing with. So that you can measure, again, the area under a velocity time graph is its distance, or its displacement. So you're measuring the amount of distance this guy has gone. And this xi is just simply in case you had a head start. You know, that again, Michael gave me the head start before he beat me in our race. We go to our third equation for this motion with constant acceleration is Vf squared equals Vi squared plus 2a xf minus xi. What was the key point about this green equation? There's no time, right? That's the key thing about this equation, is that it shows you what to do if they don't tell you how long the thing is accelerating for. But you have to know distance, right? You have to know how far it traveled, and you have to know its velocities, how fast it was going before and after. Does that make sense? Good. If I slide down here a little bit, the air resistance challenge, I want you to be able to tell me why you designed your prototypes the way you did. what you were trying to accomplish. I already asked you a question about that on your test. You should be able to explain to me why you did what you did. Does mass affect how fast something falls? It does not. Okay, the mass does not. What does affect? The air resistance, right? Because gravity pulls a feather or a stone down at the exact same speed. But a feather in our normal atmosphere here, the air holds it up. It pushes up against gravity and provides some resistance, so it falls slower. But when we take all the air out, remember our big vacuum chamber, the video we watched? They drop at exactly the same time. Doesn't matter the distance and the difference in their weight. Okay? So it's air resistance that opposes gravity and slows objects down, not the fact that it's more heavy. The mass doesn't matter. Okay? Sorry, I should have taken this off here. Newton's second law, we didn't talk about it at all. So I'm crossing that off of there. Okay? These are the exact same equations as we just looked at. They're just substituting y because we're talking about up and down motion. You can call it x and I won't have a problem with that. Okay? There's the same equations. They just change it to y when we're going in up and down motions. Doesn't matter which way you do it. Okay? What's the acceleration on our planet right here? The acceleration due to gravity? 9.80 meters per second squared. Now that does change. We'll talk about that a little bit. Okay? I did, yes. I did cross the second law. Yep, because we didn't really talk about that at all. That's the way we can measure the amount of force, which we'll talk about force in our next unit here. Okay? Any questions about this? I wasn't going to give you this, but I said, well, all right, it's one paper. It kind of gives you a summary of all the pieces we've talked about in one place. Worth having. It's going to look like problems and questions. Yeah. Problems about how we interpret the graphs. Questions about how your air resistance challenge worked. There will be some math to the problems, absolutely. Yep. Absolutely. Some short answer, some math problems. Again, that's what we did, all of those problems that we're working at. Some concept-based pieces as well. Enough that you can finish in 40 minutes, or 45 minutes, I guess we have now. I don't know off the top of my head. 20 maybe? Yeah, I don't know. Yep.
The second gravitational equation, will we have velocity?
You would choose what equation you use based upon what you're given. That's exactly correct. Okay? So if they give you velocities and distances, and you're trying to find acceleration, well, I'm going to use this guy, right? The blue one, the VF squared equation, right? If I'm given acceleration and velocities and time, and I want to find how far you traveled, well, I'm going to use the xf equals xi equation, the 1/2 at squared equation. It all depends on what you're given, guys. Remember, always three things when we look at these problems. Always three things. Number one, what are you given? Okay, what do they actually tell you? Right? And remember that time is seconds, acceleration is meters per second squared, velocity is meters per second, distance is meters. So they'll ask you, how far does it go? Well, that's meters, right? That's distance. How long does it take? That's time, right? How fast is it going? That's velocity. How does the velocity change? That's acceleration. Are you with me? So what are you given? Number two, what can you assume? In other words, is this acceleration happening on the planet Earth? Which most of our problems do. If it does, you can know that acceleration is 9.80 meters per second squared, right? Most of the time, VI is going to be 0, right? And XI is going to be 0. Most of the time. Not all the time, but much of the time. If they don't tell you about it, they're assuming it's going to be 0. Question, sir? Distance. Initial. Your initial. The I means initial. And Y just means up and down distance. Yep. Right, so if I were to give you a head start, right, that would be your initial distance would be 20 meters away from where the origin, the starting place. If something is falling, it's 9.80. Does that make sense? It's only if something's falling. A car just sitting on the ground, gravity is not going to be affecting it, right? Because the ground's pushing right up against it, so that is canceled out. It's only if something's falling, that's our acceleration. Well, G is just gravitational acceleration. Yeah. It's just the shorthand they use. Sir? So I means initial, so I think you're like the final. Exactly. Yep. Yeah, something starts at 15 meters per second and increases its speed to 25. So 25 is your final, 15 is your initial. Yep. Sir? Like on a velocity time graph, you're saying? How they relate to position is what you said? So for position, that's displacement, right? So the area underneath the velocity time graph will tell you how the position changes, right? So over, let's say this was 10 seconds, right? And this was 10 meters per second. 10 times 10, because you're taking the area underneath there, that gives you it's gone 100 meters. Does that make sense? That would look more. That would look more like this. So if we just take this top half of the graph, if we're talking about just dropping something, okay, so it would be this area underneath. And that would be 1/2 base times height to get that triangle. Sir? For the test, are we able to use time? Absolutely. I don't mind any of them, yes. I prefer an actual calculator, not your phone, but it's just much easier to work with. I'm telling you, significant digits and scientific notation is a pain in the butt on the iPhone. So I encourage you to have a real calculator, but I'm not going to tell you can't use it. Okay. Any other questions here as far as study guide? Those were good questions. I was going back to because I was giving us what our different pieces for how we solve problems, right? Number 1 was what you are given. Number 2, what you can assume. And last but not least, what equation fits those. So, what are you given? And I would also say, what are you trying to find? Okay, so what are we given? What are we trying to find? What can you assume? And then what equation fits those pieces? There were a couple of your equations that we did, a couple of the problems you did, where you needed acceleration, right? Let's say you were trying to find velocity, but you needed acceleration first, so you had to find acceleration to then find velocity. That's okay. Nothing wrong with that. Okay? But again, you say which equation, and right now these are what we got, right? It's just these equations. That's all that we've learned significantly. These guys, this guy, right? And I guess I will put the velocity is distance over time. If you look at these 5 equations, I mean, this is really what we've done as far as significant equational pieces, math pieces, for you to be comfortable with. And again, we can solve any of these for any of these pieces, right? If I need to find acceleration in this red equation, I can move the pieces around to get A by itself. And again, that's just basic algebra. I'm assuming that you're comfortable enough to do that. And again, I've seen your work. I've seen you all been able to do that. So, questions there? Okay. I'm going to stop this. Again, I assume that if you have other questions, you will ask.